Now we're going to look at spectroscopic parallax, another way of estimating stellar distances. So, spectroscopic parallax. There are two things you need to know about spectroscopic parallax. One is that it is spectroscopic, which means we need a spectroscope. A spectroscope is a device which is to look at the spectra of stars. So, the first thing is we need to analyze the spectra of the stars. The second point, it is not a parallax method. Parallax is when we look at an object from two different positions, and from the two different positions it appears to shift relative to the background. This is not a parallax, it's a badly named word. It is not. It's basically spectral analysis. It is not spectral parallax. So this technique can be applied to any main sequence star. Remember, on the HR diagram, the main sequence is the diagonal which goes from the top left to the bottom right. These are where most stars fit. And you have to be able to analyze the spectrum of the star. So two things: you need to look at the spectrum, and it needs to be on the main sequence. So here we have the HR diagram. So in other words, if we observe the spectrum and we find that the peak wavelength is there, we know that it's going to be this star. We can find out the brightness, the luminosity, the absolute magnitude of the star here. So that's good. If it was an M star, then we know it's going to be probably here if it's on the main sequence. However, there are some stars which fit this profile which are not on the main sequence. So for most stars it works. For some stars it doesn't, because there is a possibility that it exists off the main sequence. For example, this red giant here and this red dwarf here are going to have the same spectrum, pretty much, because they're both cool red stars. So spectroscopic parallax is an astronomical method for measuring the distances to stars. Well, basically what we do is that we look at the spectrum, we fit it onto the main sequence. From that we're able to find the absolute magnitude, and if we know the absolute magnitude and how bright it appears to us, we can work out the distance. It is not a parallax method. Despite its name, it does not rely on the apparent change in the position of the star from different positions. So, spectroscopic parallax. So, by matching it onto the main sequence, we can find its luminosity, or its absolute magnitude. So we know which class it is, we know which temperature it is, we know what its lambda max is. So, first of all, if we know the spectrum, that's the first thing, then we can find out using Wien's displacement law what the temperature is. Using the HR diagram, and we know the temperature, we can find its luminosity. So we have this star here, which is 5,500 Kelvin. It's somewhere here. We read off on the HR diagram, and it's approximately 1. The spectral is the luminosity approximately of our sun. Here we go. So we look at the spectrum of a star, we find this G star here, we read off, and it's got a luminosity relative to the sun of 1, because it is the sun. If you have this star here, and we look at the spectrum, we find that it's between an A and a B star, probably an A2 star. We know that it's probably going to be here, which means it's 10 to the 3 times as bright as the sun. And we know how bright it appears to us. They can work out the distance. So you have to solve problems involving the apparent magnitude, the absolute magnitude, and then work out the distance. So we need this formula to be able to do this. So by fitting it onto the main sequence of the HR diagram, we can find out the absolute magnitude. We look at it and we decide what its relative magnitude is, what its apparent magnitude is, and from this we can work out the distance easily enough. So 3.9, state that the luminosity of a star can be estimated from its spectrum. Well, this we know already. This, we look at the spectrum, we're able to find lambda max, we're able to find the temperature. From the temperature, we're able to find out which spectral class it is. We're able to find out whereabouts on the HR diagram it fits. From that position, we're able to work out its luminosity or its absolute magnitude. So if you know the spectrum, and you know the spectral class, and you can find out the temperature, you can find out the luminosity and absolute magnitude from looking on the HR diagram. When you know the absolute magnitude and you look at it, so you're able to work out the apparent magnitude, use this equation, that gives you the distance. Okay, so we have the distance. How do we find out the brightness from it? Well, the brightness is going to be equal to the luminosity divided by 4 pi d squared. So if you know the distance, you know how bright it appears to us, you can find out what its intrinsic luminosity is. The problem with spectroscopic parallax is that it's limited to measuring stellar distances less than 10 megaparsecs. This is a long way, 10 million parsecs. The other method we looked at was stellar parallax, and that's only good for 100 light years. After 10 megaparsecs, the light is so faint and it's so affected by interstellar dust that the spectrum is not very reliable. The Andromeda Galaxy is only 1 million parsecs away, so we're able to use it for everything in our galaxy and for all the close galaxies, all the stars in the local galaxy if they're bright enough. So remember, stellar parallax is only good up for only 100 parsecs. Well, actually 100 light years. The stellar parallax is only good for 100 light years, 300 light years or so. You have to be able to solve problems.